Good evening, all. Roshit sir, good evening.
Good evening, Sushmita.
Yeah, you can start the session, sir.
Okay. Students, can you ask your friends to join fast? Can you put the message in the chat bar in your WhatsApp groups and let them ask to join? In the meanwhile, while I share my whiteboard. Okay, so very good evening, students. Very good evening. Can I get a quick heads up in the chat box if you are there? Good evening. Good evening, Pravalika. Good evening, Suyash. Good evening, Snehal. Good evening, Kajal. Good evening, Vinith. Good evening, Gomatesh. Good evening, Jinat. Good evening, Sanjay. Good evening, Sandhya. Good evening, Maskan. Good evening, Anu. How are you all doing? Okay, so any assignment is given yesterday? Yes, no. Good evening, Tanisha. Good evening, Aryan. Okay, so today I'll be discussing the remaining part of trees. Okay, we were continuing trees, right? There we were discussing traversals, right? We stopped it there. So we will discuss this traversals part and two LC problems, two lead code problems on trees. Okay, two lead code problems on trees, and then I will be discussing BST, binary search tree. Okay, and then inserting a node into binary search tree. Okay, and then I will be discussing. Good evening, Anurag. Good evening, Mangesh. So then I'll be discussing validate BST1 problem as well, LC problem. Okay, and then I will go with the graphs. I will start the graphs. Okay, so in graphs, I will be discussing the terminology. Okay, the terminology around the graphs, and then I will go with the BFS and DFS, traversal of graph, the most important part in graph, BFS and DFS. Okay, so this will be the agenda for the next 1 hour 45 minutes. Okay, so before that, yesterday I have given one assignment to you, one problem, one important problem, that is trapping rainwater. Did anyone do this? Did anyone do this? Gomatesh, okay, good. So what is the time complexity of your code, what you have written? Gomatesh? Only Gomatesh has done or anyone has done still this question? Snail, Anurag, Shaik, Suyash, Sandhya, Vani. Okay, so what is this question telling? What is this question telling? What is this question telling? So basically, let me explain the question first. So given non-negative integers representing an elevation map where the width of each bar is 1, and compute how much water it can trap after raining. Okay, so if you can see here, here it is 0. Okay, here it is 0. From 1, from 1 to in between, the blue color is there. That is nothing but your stored water. Okay, so if you can see, 1 is a building height. This one is of 2 height, and in between you have the 0. So means if you can see the building, top building you have and a smaller building you have, then only you can accumulate the water here, right? So when you have the smaller building, when you have the bigger building, then you can accumulate the water between. Then you can accumulate the water between. Okay. So if you accumulate until this point, then it will flow off, right? It will flow off because there is nothing here. There is nothing here. So it will flow off. So like here also, if you can see, here also, if you can see, like this is of 1 height, this is of 2 height. Okay, 1 and 2. So how much water will be stored here? How much water will be stored here? This is of 1 height, this is of 2 height. So basically until the minimum height it will store, minimum height of other building, right? Until the minimum height of other building that it will store. So what is the minimum height of 1? It is 1, right? So 2 minus 1, you can take it as 2 minus 1, which is nothing but here 1 water will be stored, 1 unit of water will be stored. Okay, and then every unit I should consider. Okay, then here also if you see, here also in between the building, this is of 1 unit, this is of 1 unit. So how much water will be stored here? How much water will be stored here? Plus 1, right? Plus 1 will be stored. And if you can see here, here and here, here and here, between this. So this is of 3 units. This is of 3 units, right? This is of 3 units, and this building is of height 2 units. So how much water will be stored here? 1 unit of water will be stored, right? Here also 1 unit of water will be stored, and if you can see in between this, so this point, until this point means until this height, so it is plus 2, this one is plus 1. So how many water is stored until now? 1, 3, 4 and 5 units of water is stored until this point. Yes, and then if you can see here, this is of 2 height, this is of 2 height, and this is of again 2 height. Okay, in between you have the 1, in between you have the 1, means 2 2, same. But here if you can see the height of the building, you should calculate. Height of the building is 1, so how many units of water you can store? Only 1 unit of water you can store. Okay, so here it will not store because it will flow off. Means if you see the understanding here, there should be one small building, there should be one big building in the right side. Okay, either in the left or either in the right, there should be one minimum building, there should be one maximum building, then the water will be accumulated. Otherwise the both should be same. Here also it should be 2, here also it should be 2. If the building is not there in between, then the water will store in between, right? Otherwise the height should be same. If the height should be minimum or height should be max in the right side or left side. So height of the building should be before buildings. So if you are considering some this like some nothing is there here. Okay, nothing is here. Zero building, zero height building. So what you should do in the previous anything is there height building you should check. So max height building what is there you should check. So basically suppose some 1 unit of building is there here. 1 unit of building is there as a max height before. Okay, immediate before. Okay, and here also you have some 2 units of building, 2 units of building. So this is of max building. In this you should check what is the minimum building. This is a minimum building, means the until minimum building point only it will store, right? So you will take the minimum, you will take the like after this, which is a minimum, this is a minimum, right? So many units of water will be stored now. So 1 minus 0, what is this building height? It is 0, right? So 1 minus 0, which is nothing but 1 unit of water will be stored. You are understanding intuition? Yes. So what you need to do, you should consider, suppose you are considering this 0. What is the left to max? You will be considering what is the left to max. And you will be taking out the right to max as well here. The right to max also here. Okay. And then you will calculate the water unit. How you will calculate? Out of that which is minimum. Either left to max is minimum or right to max is minimum. Okay, either left max is minimum or right max is minimum, and then you will subtract the current building height, the current building height, This will be the water unit. Okay, like this you will keep on calculating for each and every height. You will keep on calculating for each and every part of the array until big of n, until the end of the array. You will calculate this one. You will calculate this formula, and that will be the answer. Okay, water plus is equal to minimum of L max, right max minus current of I. Okay, So we find that this place is empty or not. Yes, so you don't need to find also. If it is zero, anyways it will be, the current height will be zero only here, and the left to max is some 1. Okay, this is 2. Suppose on the right you have the 2 height building, on the left side, on the left you have the 1 height building. So in this case, what is minimum here? 1 only, right? So 1 minus 0, which is nothing but 1 itself. Yes, so basically if both left and right heights were there only, then only water will trap in between, right? If height like if some greater than that, greater than this building, some height is there only. Suppose if you can see here, suppose this height is 1 now. Okay, this height is 1. Greater than this building, some like suppose like here, like you have the 2 height here. Okay, you have the 3 height here. Okay, this is of 3 height, this is of 2 height. Okay, so for this you need to calculate now. For this you need to calculate now. So means you will find out this is a maximum height for this building. Greater than this one is there. Greater than this, greater than this, on the right side you have this 3 units. Whereas greater than this, greater than 1 unit, in the left you have the 2 units. You have the 2 height. Okay, 2 feet height. Whereas on the right you have the 3 feet height building. Okay, but whereas the current building is of height only 1 feet. 1 feet. But until where the water will trap? Only until the minimum height of the building, until the minimum until this point on, until the previous building, until the left building only it will trap. If you fill this until the maximum building also, what will happen? It will flow off. There should be some level. There should be some level in between, right? There should be some level in between. If you can if you fill this one also, if you fill this one also, it will flow off, right? It will flow off until the height. So you cannot keep until the max height on the you need to check which is minimum in this, which is coming to the level. Okay, so like that you will be checking out. Okay, so what is the thing? You will find out the minimum of this, either 2 or either 3. So 2 is minimum. Then for this current building, right, you will minus that. So that will be the left out water, because you cannot fill this building with water. On the top terrace only you can hold the water, right? So for that reason, that one. Okay, so basically what you need to do, suppose the it is like this: 0 1 0 2 1 0 1 3 2 1 2 1. Okay. So now what you will be doing, the first one is like some brute force approach. What you can do, for everything you need to calculate this formula, right? Minimum of left to max minus right max. That will be the answer, right? Right max minus your height of the building, current height. Current height, what was there? That height of the building you will be calculating for every building. So what I should do first, I should like I can take brute force approach. Like I will be traversing forward. I will be traversing forward until the end for finding out the current one in one loop. Okay, in one loop, and then I will take another loop. I will take another loop. Like I will in one loop I will find out the max as well. While going forward, I will find out the left to max as well. Okay, I will consider this as left to max for now, and then I will start the loop from here. I will start the loop from here. Current max is this one. Then I will minus this. Like that I will go. Otherwise, I will take another loop. Otherwise, I will take another loop. I will take one outer loop for calculating the for traversing as well. I is equal to 1, I less than n, I plus plus. Okay, and then inner loop. Here I will initialize before itself. Left to max is array of 0. Array of 0. Okay, array of 0. Then I will check whether left to max, like whether I will check max of, okay, max of left to max or your current of I, your current array of I, whether this is max or this is max. I will check it. I will check it whether this is max or this is max. Then I will also, this will give the left to max, and then right to max is, and then right to max is, and then again I will take another loop that will start from I is equal to n minus 1. Okay, I is equal to n minus 2, I less than or equal to 0, I plus plus. I will start from right as well. I will put right max as 1, right? This one I will take it up. 1. This max, this one I will take it up. And then I will again find out the right max like this, right max. Okay. Right max comma, current of I, current of I. If it is not true, if it is, then I will find out then I will find out minimum of this formula. I will put it up. This formula I will put it up for the answer. For the answer. So this is left to max, comma right max minus current of I, minus current of I. Like this, I will calculate the answer. Okay. So what is the time complexity of this? What is the time complexity of this? We go of n square, right? I am moving forward. For everything, I was calculating right max. Okay. So this will be big O of n square. Okay. Can I do it in big O of n? Can I do it in big O of n? Is that possible? Is that possible? Yes or no? Can I do it in big O of n instead of n square? Big O of n. So what I will do? What I will do? I can go with the prefix approach. Okay, I can go with the prefix sum approach or prefix max approach and suffix max approach. Okay, so I will take two arrays. I will take two arrays. I will start one array, the prefix one from starting. Okay, so prefix one from starting. So suppose what is the max here? It is 0 itself, right? I will put it as 0. Here what is the max? Here it is 1. Here it is 1. And then here what is the max? It is still 1. It is still 1 itself, right? And here what is the max? It is 2, right? It is 2. And then here what is the max? It is 2 itself. Okay. And here what is the max? It is 2 itself. And here what is the max? I've got until this point. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Here what is the max? Here it is again 2. Right? Then here it is 3. So all the things will be until this point it is 3 itself. Right? 3. So 1, 2, 3, 4. 1, 2, 3, 4. So like this, I will calculate the prefix max. Okay. Prefix max array. Okay. And then suffix max also I will calculate. Suffix max also I will calculate from last. From last. So what will be the last one? So I will take another array. So it is 1 year, it is 2 year, and it is again 2 year. So I'm coming from last. Okay, 1, 2, 2. Okay, 1, 2, 2. And then again 2. And then again 3. And then again 3. 3. And then 3. And then 3. Like this, it will go on until 3 itself. Okay, it will go on until 3 itself. Then what I will do? I will take another loop after calculating prefix and suffix. I will take another loop for calculating this answer, for calculating this formula answer. So what I will do? I will start the loop from 0. Okay, this is your current of I. Then I will check here. This is minimum or this is minimum or this is minimum. Here 1 is minimum or 0 is minimum, right? So 0 minus 0. The answer will be 0 itself, right? Then again I will move 1, 1. So here I will check 1 and 2, which is minimum. 1 is minimum. So 1 minus, like 1 minus 1, which is again 0 itself. Then again I will go 0. 0 is, what is the max here? So this is 1, right? 1 and 2. Again 1 itself. So 0 minus, like 0 minus of 1, which is minimum. So 1 minus 0. Again it will be 1 minus 1 minus 0, which is nothing but it will accumulate 1. So like that I will keep on calculating the formula, which is minimum minus current of I. Okay. So what is the time complexity of this? What is the time complexity? You will get it up. What is the time complexity? You will get it up. So I will use one loop. I will use I will use one loop. Okay. Okay. I will use one loop for prefix, for finding out the prefix, where I start from, like from 0 to n. Okay. Then for finding the suffix, again I will start the loop from here. So here n minus 2 to until 0. Okay. One loop for 1 to 0, one loop for 1 to n minus 1. Okay. And the other loop for 1 to, like n minus 2 to, I will start from end, right? N minus 2. I have one n minus 2 to, like your 0, the other loop. Okay. Then after calculating the suffix, I will run the loop from 0 to n. Okay. For calculating this formula. So the complexity will be big of n for this. Here also big O of n. Okay. Big O of n. And for this also big O of n itself. Okay. So which is nothing but you can take it as 3n, and you can take it as this one as a big O of n itself. Okay. You can take it as big O of n itself. Okay. You're doing 3 passes, but the thing is you can take it as 3n. But the thing is, in the worst case, you will calculate the average case, right? So in that case, big O of n itself. Okay. So this will be the complexity of this. Like this we will do using prefix and suffix array. Okay. So next one, optimal approach. What you can do, direct, I will take a two-pointer approach. Okay. Two-pointer approach. Here we are using space complexity. In your prefix and suffix array, space complexity you say. So one for prefix, one for storing suffix as well. Okay. So this is space is wasting usually for you. So if you use a two pointer, you can do it in big of one. So how to do it in two pointer approach? 420, 325. Okay. 420, 325. So what I will do, I will take a L here. I will take a R here. Okay. I will take a R here. And then what I will be doing, I will check whether, like within this, like I will run the loop from starting itself. Okay. Now this is your current of I. Then I will check whether this is minimum or this is minimum. Our formula direct. Okay. So 4 is minimum, right? 4 is minimum. So in this case, I will do 4 minus 4, which is nothing but 0 unit. 0 unit. Answer is 0. Okay. Then I will move the left pointer forward. Okay. I will move the left pointer forward. And then 2 and 5, which is minimum, 2 and 5. I will also move the current of I. Which is minimum of this, 2 or 5. 2 is minimum, right? 2 is minimum. So in that case, again it will be, Okay, sorry. Uh, okay, I will be taking initially left to pointer as 0 itself. Okay, left to pointer as 0 itself, left to max as 0 itself, and right max also as 0 itself. Okay, then I will be checking, I will be comparing this with this and this with this. Okay, this with this and this with this, and then am I going wrong or okay, I'll be comparing this with this. Okay, this with this with this. Okay, so now you tell me like 4 and 0. This is max, and out of 5 and 0, this is again max. Okay, now this will become the left to max. So 4 will become the left to max, 5 will become the right to max. And then now what you will be doing, which is minimum, you will check. When this is minimum, you will just you will run the loop again from I. Okay, I is equal to 1. Okay, I is equal to 1. So 2 minus 4. Okay, so 4 minus 2, which is nothing but 2 watt, 2 units of water it will accumulate. And then you will move the left pointer. You will move the left pointer forward. Okay, you will move the left pointer forward. And then you will go to the 0. For this 0, like 2 and 5, which is minimum, 2 is only minimum. So what will be the case? 2 minus 0, which is nothing but 2 itself. Okay, plus 2 will be added. And then again you will move the left pointer here. Okay, 0. This is 0 itself, right? This is 0 itself, and then you this is your current, right? So out of this 0 and 5, which is minimum? 0 is only minimum. 0 is only minimum. So you will calculate it. Let me do the logic, you will understand. So I will be taking a left to max as well as the right to max. Okay, I will be taking the left to max as well as the right to max. So what I will be taking, I will be taking result array. Okay, that will be initialized to 0, and then I will be taking left as well. Okay, left to max, you can take it as left to max is equal to 0 only, and right to max also is 0 itself. Okay, and then I will be checking like your left also. I'll be right, you will be taking the left to max and right max as 0 only, and then you will start your pointers also. Starter pointer will be starting from r is equal to n minus 1. Okay, r is equal to n minus 1 means last one, and l is equal to 0. Okay, and then you will be checking while L less than R, while L less than R. Okay, so you will be checking this with this with this. Okay, this with this. So you will be checking left to max. Then what will happen? Left to max will be like you will be checking that also, whether like left to max, this is greater, this is greater, or the left is greater. Okay, so left to max comma your height of I. Okay, your height of L. Okay, height of L. You'll be checking, you'll be comparing this with your left to max. So what is the max now? It is 4 itself, right? It is 4 itself, right? And then you will be calculating the right to max as well. Right to max is max of right to max is max of right to max comma, okay, right to max comma height of R, height of R. Okay, Then what you will be doing? Then what you will be doing? Then you can, what you can do? Then you will also again check. You can again check if left to max less than right max. If left to max is less than right max, then what you can do? You can directly take out the left to max itself, right? So plus result is equal to result plus, okay, you'll be attaching the result plus, then left to max, okay, left to max minus height of I, left to max minus height of I, okay. Else, what is the condition you will be checking? You will be taking the right to max, okay. You will be taking the right to max minus height of I, okay. Then you will be returning the result. Then you will be returning the result. This should be outside. Then you can just return the result. Okay. Then you can do L plus plus R minus minus for this. L plus plus R minus minus. Okay. So like this, you can calculate the height dot length minus 1. Height of L only, right? Cannot find symbol height. Why height? Height I have written wrong or what? Height of L itself and then height of R itself. L max. Okay, here you will be checking the max of the thing, right? Okay, the max of red dot. You will be checking the max, right? L max and then R max, correct? Here also R max, then height of R max, then R max minus height of I. Okay. R max, L max, height of L, height of R. Okay, okay, this one, mat or max. Think so before. L max, okay. Result plus L max minus height of L, right? Height of L and height of R. Okay, passed. Then I click on submit. Okay, passed. So I am sharing this code with you all. If you are having any issues still, let me know. In the end, I will again try run. If you are having any issues with this code, let me know. I will do the dry run again in the end. Okay. So let me go back now. It's already 7:50. We need to complete much. Okay. Okay. So what we are discussing in the last class, we were discussing the trees, right? So trees. Where is the tree here? Okay. So what is a tree? Basically, you will have the like this. So one node is connected to multiple other nodes in hierarchical fashion, right? So the top node is always called the root node, whereas the inner nodes, what were there, like you have a parent node here, and then what are the new nodes that were attached, those are called as your child nodes, right? And then the outer nodes, what were there, the last nodes, the last level nodes are called as your leaf nodes, right? And then you will have the levels. So you can consider this as your first level, this is your second level, or this is your third level. Okay, so you can consider it as a level. Okay, levels. And then height of the tree in the sense the level of the tree, and you can consider the depth also. Depth in the sense you are moving from root node to leaf node, that is nothing but the depth of the tree. Okay, so then we have the different types of trees. So full binary tree in the sense either all the nodes should have either zero nodes or two nodes. It should not have one node, or it should not have three nodes like that. It should have either 0 or 2. For every node, there should be either 0 or 2 child nodes. Okay. Then complete binary tree in the sense, all like complete binary tree in the sense, all nodes, like all nodes should have at least two nodes, or two nodes. And then in the last end, you can ignore. In the last end, you can ignore. In the last level, you can ignore. But the thing is, every node should have at least two nodes. Okay. Then a perfect binary tree in the sense all leaf nodes should be at the same level. They should be at the same level. It should not be there like this. They should be at the same level. And then balanced binary tree in the sense if the suppose eight nodes we want to place, then you can place it in 2 power 8, which is nothing but 4, right? So you can place it in like four levels, three levels basically. You can place it in three levels. So it should be of log to n format. It should be of log to n format. And then you have the degenerate tree. Degenerate tree in the sense it's like a skew tree where you will have one child only for one parent. For every parent, you will have only one node, one child node. Okay, that is nothing but a degenerate and tree. Okay, then we were discussing tree traversals. Tree traversals. So tree traversals, be either it can be BFS or either it can be DFS. Okay, so in BFS, so BFS is nothing but the level wise traversal. Okay, whereas in DFS, depth first search, we have the in order, pre order, and post order. Okay, traversal in the sense I'm moving from one node to another node. Here we have these three types of DFS traversals: in order, pre order, and post order. And then BFS is nothing but the level order traversal. Are we clear until this point? Yes, everyone. Yes, everyone. Are we clear until this point? Okay, let's continue the tree traversals. Okay, so what were tree traversals were there? So basically, it is divided into two parts, that is BFS and then DFS. So let's take DFS now. So in DFS, we have the three types, that is in order, pre order, then post order. Okay, then post order. In order, pre order, and post order. So in the case of in order, you will have the left node, we have the left node, we have the root node, and then you have the right node in the case of your in order. Okay, in the case of a pre-order, you will have the root node in the beginning. Okay, you should traverse root node first, and then you will be traversing left node and then right node in the case of your pre-order. And in the case of a post-order, you will be traversing left node, right node, and then you will traverse the root node as well. Are we clear until this point? Yes. So let me draw a tree. 1, you have the 2, you have the 3, the 4, you have the 5, then you have the 6, you have the 7. Okay, and then here you have the 3, you have the 8. Okay, you have the 9, and then you have the 10, 11, 12, and then 13. Okay, and then 13. So are you there with me, guys? Yes, can I get a quick heads up in the chat box? I'm not able to see your messages. Okay, okay, good. So I want to convert this into in order. I wanted to do the in order traversal. So in order traversal, how you'll be doing? You'll be traversing first left node, then root node, then right node, right? So let me write left, root, and right. Okay, let me take another color. Okay, left, root, and right. Okay, so now for this left is there. For this left is there. Yes. So I will traverse here. Again, here also left, root, right. Then again, left is there for this. Yes, left is there. Left is there. So again, I will move to the left. For this, again, left is there. Yes, left is there. Again, I will move to the, here left is there. Left is there. No. Okay. Left is not there. So I will traverse to the root node. I will traverse to the root node. I'll print that answer here. Okay. First one, 10. And then right is there. Right is there. No. Okay. Right is not there. Then what I will do? Again, I should move to the, I will backtrack to the root node again, 8. Okay. So I will print out this 8 here. Okay. Then right is there. Right is there. Yes. Right is there. Okay. Then again, left is there. No. Right. Root is there. Yes. So 10, 8, 11. Okay. 11 will be the answer. And the right is null. Then again, I will backtrack. This is already completed. Then again, I will backtrack. So here root node. Okay. So 2. Okay. And then right is there. Yes. Right is there. So again, I will go to the this node. Left, root, right. Left is there. Yes. Left is there. I will go to the this thing. Here left is there. No. Root is there. Yes. So 12. Okay. 12. 12. And then what is there? So your right is not there. So it will be done and it will backtrack to the 9. Your root is there. So 9 and then right is already, right is there. Yes, I will move to the right node. Left, root, right. Left is not there. Root is there. Okay. I will print 13 here and then right is not there. I will again backtrack. I will again backtrack. I will again backtrack to the root node. Here root, I will be printing it up 1 and then right is there. So I will move forward. I will move forward. Again left, root, right. So left is there for this. Yes, left is there. I will move here. And then here also again left, root, right. Left is not there. Root is only there. So 4, right is not there. I will again backtrack to 3. Okay. Again root, I will be printing it up. So 3, and then right is there. Yes, I will go here. Left, root, right, and then left is there for this. Yes. So I will go here. Left, root, right. So again, what you will do? Left is not there. Root you will be printing it up. Okay, root you will be printing it up. Right is not there. Okay, I will again backtrack. I'll be printing root 5, and then again right is there. I will again go forward and left, root, right. So left is not there, root is there. So it will be 7. It is like this. What happened? Why it is doing like this? Okay, it got stuck. Yeah. Then this. Okay, 6, 5, and what is the next answer? That is 7, right? 7. Why it is doing like this? Okay. Okay. Again, it went like this. Yeah. So this will be the in order traversal. Okay. 10, 8, 11, 2, 12, 9, 13, 1, 4, 3, 6, 5, 7. Okay. So again, pre-order. Pre-order for this. Pre-order for this. So let me rub this up. So in order in the sense, you will traverse the left node first, and then root node, and then right node. In the case of pre-order, what you will traverse? Can you tell me fast in the chat box? In the case of your pre-order, what you will traverse first? What you will traverse first? Can you please reply in the chat box? Is the time now 8 o'clock? Okay. In the case of pre-order, you will traverse first to the left root node, right? Root node. So what is the root node here? What is the root node here? 1, right? Then you will traverse the left node. Left node, right? This is again the root. This is again the root. So 2, and then this has the left, right? So this is again the root 8, and this has again the left. This has again the left. So that is again the root node. This has no left. So it will backtrack. It will backtrack to root node. Then what you need to do? You need to traverse a you need to traverse a right node, right? Right node. So it will go here and it will bring me 11. It will bring me 11. Okay, then again it will backtrack. Then again it will backtrack. Again it will backtrack. Again it will backtrack. Okay, this is all. This is again all. Your right is not completed. It will go here. So it will bring me 9. It will bring me 9. Then again it will go to the left. It will bring me 12. Root node. It will bring me 12, which is root node. And then 12. 12. And then again it will backtrack and it will go to the 13. It will go to the 13. And then again yeah, again it will backtrack. Again it will backtrack. Again, it will backtrack and it will go to the next node. Okay, here it is a root node, which is 3. Okay, here it is a root node, which is 3. It has a left, which is 4. Okay, 4. And then again, it will backtrack. It will go to the right node, okay, which is 5. Then again, it will go to the root, which is 6. Then again, it will go backtrack and it will go to the 7, which is the right node. Okay, so this will be the pre-order traversal. Pre-order traversal. Are we clear until this point? Yes, everyone? Give me one moment. So can you quickly, while I come back, can you quickly give me the post order answer as well? Post order in the sense you will have the left node, you will have the right node, and then you will have the root node. Can you give the answer for this? Can you give me the answer for this? Okay, left, right, and then root. Okay, can you provide the answer for this? Okay. So Rani has given the answer. Maud has given the answer. So Yash, where is your answer? Post order. So post order, what is the, so you need to traverse first to the left node, right? So you'll be traversing first to the left and then right and then root, right? Left root and left right and root, right? So exactly you'll be traversing left root and right. Left root and right. Okay. So what is the answer for this? It will be, you'll be traversing from this end, from this end. No, so this has a left, this has a left, and this has a left. So the answer will be for this 10. Okay. Then you'll be traversing 11. Okay. And then the root node 8. Okay. And then you will be going to the backtracking to the next one. But before you should also take, so 10, 11, 8, and you'll be backtracking to 2. This has the right node. So what you need to do, this has again the right node. So 12, 13, okay, and then you'll backtrack and then you'll print 9 and then 2, and then you'll be backtracking to 3, and this has 4, okay, you'll be printing 4 and then 5 and then 5, oh not 5, so you'll be printing 5 and then this is 6, right? So 6 and then 7 and then 5, okay, and then 3 and then 1. So this will be the post order traversal. Okay, so let me discuss the code, how you will do this, so any problems if you are doing the traversal, and if you are backtracking it, means backtracking in the sense you are visiting only once. Okay, so you are again visiting that node, that particular node, and then you are again moving forward to the next node. So when you are following the backtracking problems, definitely you need to go with the recursive calls. Okay, definitely you can go with the recursive calls. So I will explain one of the thing. So I will explain the code for this in order. Okay, in order. So we will be doing the code for in order. So suppose class tree, okay, tree traversal. In this, you're finding out the in order. Okay, in order, you will be getting the first node. Okay, you will be getting the like node. Okay, node of something like head. Okay, the first node, the root node, or else you can take it as root node itself. Okay, root node itself. So what you need to do, so first what you will be traversing, you need to traverse the left node, left one, right? So in order of, you will again call that recursively in order of root dot left, root dot left, root dot left. Then you will print out the system dot out dot println. You will print out the root dot data. Okay, you will print out the root dot data. Okay, root dot data, and then you will again traverse to the right node, right? You will again traverse to the right node, root dot right, root dot right. So this will be the code for your in order traversal. In order traversal. It's not coming. Okay, this will be the code for in order traversal. Can you tell me for free order? Can you tell me for free order? Free order how it will be? In the pre-order, first you'll be printing the data, root dot data. Okay, and then you'll be printing the in order, root dot left, and then Okay, pre-order, right? You can take a pre-order function and then you will again pre-order to root dot write. Root dot. Okay, so like this, you can do the pre-order. Okay, you can do the pre-order. So basically, you're taking, like, if you wanted to represent, you're taking as a linked list only. You're taking as a linked list only. This is your data part. This is your left part. You will take it as a double linked list structure. Okay, you will take it as a right node address. You will take a right node address. Okay, then you will again put a data here, and then left, then right, left, right. So like this will form of the linked list. Okay, so what you will be forming the linked list? So class node, you will have the data part into data, then you will have the node left. Okay, node left, and then node right reference as well. Okay, so initially the node will be in the constructor. What you will do in the constructor, what you will do, you will take the data. Okay, this dot data is equal to data. This dot data is equal to data. Okay, this dot data is equal to data. Then left and right will be null. If you wanted to insert the first node, what you will do? Node, suppose node new is equal to new node of new node of some 10 you are given. Some 10 you need to insert. The first node this is. Okay, so you'll be calling this, and then the right node will be null. Okay, like new dot, left will be null, right will be null. Suppose if you're inserting the second node, you're inserting the you're inserting the second node. So what you will do, new dot left is equal to new node. Okay, new node of 70. Suppose you are inserting this as root dot left is equal to new node. Then again root dot right is equal to new node. Like this you will go on inserting the things. Okay, so this is how you will represent the tree in linked list format. Okay, are we clear until this point? Are we clear until this point? Yes, everyone. Can I get a quick heads up in the chat box? Okay. So let me now go into one lead code problem. Identical trees. Same tree. Okay. So if you can see this problem, so given the roots of the two binary trees, P and Q, write a function to check if they are same or not. Two binary trees are considered the same if they are structurally identical and the nodes have the same value. And if you can see the problem here, So if you can see, so basically they are asking to check whether the both of them are same or not. Both binary trees are same or not. Same or not in the sense, they should have the same data as well. Okay, here also 2, and the left node has again 2. And right node has 3, They are identical. So this will be true. Okay, so how they will give in the question is, they will give first the root node, and then the left node, and then the right node of it. Okay, like this they will give. So if you can see, 1 is the root node, 2 is the left node, 3 is the right node. 1 is the root node, 2 is the left node, 3 is the right node. Like this, they will give it. Okay. So if you consider this, is this equal? Is they are identical? These are identical? Yes or no? These are identical? Yes or no? Properly observe. See, what is the root node? The root node is 1. Okay. On the left, what was there? On the left, it is 2. Okay. On the left, it is 2. Here also, the root node is 1 itself. Here also, the root node is 1 itself. But the left is null. Means nothing is there here. Whereas in the right, but here the left is 2 is there. Here only it is failing. In the left it is 2, here it is null. So it is false. Whereas in the right you have the 2. But in the right you have the 2, but here you don't have any right. Here it is null. Here also it is failing. So it is not identical. Not identical. Okay. And let me go to the next. Can you tell if this is identical? Quickly. Can you tell this is identical? You have the 1 root node. Here also 1. Here also 1. Correct. And then left node, what is there? Left node, what is there? 2 is there. Here also left node, you see. Left node, it is 1, not 2. So they are not identical. Okay. So identical in the sense what you should have? You should have here also 2 itself. And here it is 1. Here also you should have the 1 itself. That is meant by the identical. Both trees are should be same. Are we clear until this point? Yes. So how can I do this problem? How can I do this problem? While explanation only you would have understood, right? So can I apply a traversal? Can I apply a traversal? Any of the traversal? Yes, can I apply a traversal of, you have the three traversals, right? In order, pre-order, post-order. Can I apply any of the traversal here? Yes or no? Yes or no? So if here I'm applying in order, here also what I should apply? Here also what I should apply? Here also what I should apply? I should apply same or different traversal. I'm not getting answers in the chat box. Same or different traversal I should apply. Same traversal I should apply. So here also in order I'm applying. Here also in order I'm applying. So what I will do in order in the sense first I should traverse the left node, right? First I should traverse the left node. So left I'm checking. I'm coming here. Whereas left is here. So I'm checking left node. So there is no null. Here it is null. Left is null. Here also it is null itself. Here also will come. I will check whether it is null. And then here it is 2. Here left node, here root node is 2. Okay. Then I will take another array. Here I will compare with 1. Here it is 1. So I will compare this both data. I will compare the both data also. The left node and right node. They are not true. They are not true. So I immediately will return the false. Immediately I will return the false. Okay. Suppose in this case, the top one. The top one, this one. Okay. So first, suppose I'm applying pre-order only. Pre-order only. Okay. Pre-order only. Pre-order in the sense, first I should traverse a root node, right? So what I will do, I will compare root node data. Root node data. Same, same, right? If it is same, then I will move forward. I will move forward again to the left. I will again move to the left. So here it is. Left is not there. So for this node, left is not there. So only root is there. So I will again check. I will again check 2, and here also it is 2 itself. Yes, correct. It is correct. I will again move forward. I will again move forward to the right. So I will again backtrack to the root node, then again right. Okay, here it is 3. Here it is 3. Here also it is 3. Here also it is 3. This is also perfect. So I will just return the true now. When all the conditions are passing, I will just return the true at the end. If if one of the condition has failed, then I will directly return the false then and there itself. Did you get the intuition? Yes. Yes or no? Yes. Yeah. Can you try solving this? Can you try solving this? So I will open up the editor directly. Yeah. So what I should be doing first, I should check each and every node, right? I should check each and every node, right? Okay, what I should be doing, I should be checking each and every node through your pre-order or in order. You should apply for P also. You should apply in order. If you're applying for first tree, you're applying pre-order. For the next tree also, you should apply the pre-order only. Okay, like that you should do. Like that you should be doing, right? So first, what I will check if nothing is there, empty is there. If p double equal to null, if p double equal to null, okay, and p double equal to null, and q double equal to null, q double equal to null means the nodes are empty, the trees are empty. Then in that case, directly I can what I can do, I can return true. I can return true, right? I can return true. Yes. If the next two case, if suppose p is double equal to null, p is double equal to null means the right tree is empty, the right node, the root node is empty, but q has something. Okay, the q has something. Okay, so r q double equal to null, either of the ones are empty, either of the ones are empty. Then what I should return? Can I get a gets up in the chat box? What I should return? I should return false. I should return false because they should be same. They should be either both should be null or one of them should not be null. It should not be null. Okay. So I'll be returning just the false itself. And if p double equal to null, p double equal to null. So then what I will be doing, if these are the base conditions, I will be checking first, and then I will perform my traversal. I will perform my traversal. I'm performing the pre-order traversal itself. Okay. So what I will do, so I will check if if r1 like your p dot data double equal to q dot data, and what you should do now, you should do the traversal of left node and right node, right? You should do the traversal of left node as well as right node. So what you should do, you should call the same function again. You should call the same function again. So is, you should call the same function again. Okay, is same tree, is same tree, is same tree of p dot left, p dot left, p dot left double equal to q dot left, q dot left, and and is same tree, is same tree of p dot right. Okay, p dot right double equal to q dot right. Okay, double equal to q dot right. Then what you need to do, just return true itself. It will keep on traversing. It will keep on traversing. Like your traversal, how you have done, it will keep on recursively traverse. First, it will traverse all the left nodes. Then again, it will check the data of everything. And then again, it will traverse the right node. And if everything is equal, then it will return me the true. Otherwise, it will return me the false. Okay, otherwise, it will return me the false. Okay, so these are the things you should be checking. In the end, you can In the end, you can return the false condition. If none of the this is not working, then you should return the false itself. Okay, so let me check whether this is working. Compilation error again. Okay, any bracket is missing. And is same tree of p dot left, correct? Okay, here also traces. Okay, then p double equal to null, q double equal to null, and p double equal to null, correct? What I am doing here, why I am checking this, what I am doing here. Please, when I'm making mistakes, please inform me in the chat box. Not attendance is not important here. Okay, solving problems is important. What is what you are getting? Same tree p1 dot data. How they have represented the data value. Okay, value. Okay, here also value. Okay, you should check, guys. They will give the driver code as well like this. Okay, you should check the driver code. Means they are following the same pattern in your main method. Okay, you should check this pattern. Value and then left and then right. They will do this convention. Okay, so like this. Okay, value then left and then right. Okay, so let me true, false, and is same tree. One extra high where one extra high. Q dot right is same tree, correct. Okay, passed and then submit. Okay, passed. Right. So I'm giving this problem to you for practice. Okay, just I'm doing the traversal on both the trees. I'm doing the traversal, and while doing the traversal, I'm checking. I'm checking before itself whether the values are equal, or is there any mismatch, whether it is null, or it is there is a value is there, or both the trees are null, or one of the tree is null, one of the root node is null. Like that, I'm checking before itself. Okay, so that is understanding here on this thing. Are we clear with this problem? Yes, everyone. Are we clear with this problem? Yes, everyone. Yes, no. Okay. So on this type only, I will give another model problem as homework to you. Okay, as assignment to you. Symmetric tree. Okay, symmetric tree. So the same model you can apply. Okay, but there will be some change. I will not be saying the change. You do it yourself. Okay. So what is symmetric tree means? Symmetry in the sense mirror tree. Mirror tree. It should be same. Okay, mirror tree means mirror in the sense I will be there. So if I'm looking, if I'm seeing at you, you are the mirror to me, right? I may look right side, right? I may look right side to you. Okay, for me it is left side. If I am the mirror to you, then I will be looking to you as right side, right? In the same way, here also, if you see the off part of the tree, I can take it as the symmetric. Okay, on the off part of the tree, I can take it as a symmetric. The off part of the tree, I can take it as a I can off this part from root node. I will off this part. Okay. So root node anyways, I will leave this up. And if you can see, if I flip this, means if I fold this tree, then it should be same. And if I fold this tree, it should be same. So if you can see, two, here also two. Okay, here also two, only one node. It will be same anyways. It will be same. And when I fold this, this 3 is on left side, this 3 is on right side. When I fold this, whether 3, 3 will be overlapping or not? Will be overlapping or not? Can you tell whether it will overlap or it will not overlap? Yes or no? Pick answer in the chat box. Whether 3 will overlap or not when it is folded. When this paper is folded. If you consider this first half of paper and this is second half of paper. When this is folded, then like this it will come, right? Like this it will be folded. Then 3 will be overlapping. Yes, 3 will be overlapping because this is on the left side and this is on the right side. It will overlap. And then 4, whether 4 will overlap with 4 on the right side, on the left side. This is on right side, this is on left side. Whether it will overlap? Yes, it will overlap. Yes. So what is the answer now here? It is true. It is a symmetric tree because on the left side it is overlapping with the right side. So it is a symmetric tree or a mirror tree. Are we clear? Are we clear? So they are given, see, this 1 is a root node and then 2 is a left node and again 2 is the right node, then 3 is the left node, right is 4 and then 4 is left. So if you can see, 2 is the root node, 2 is the right of this and then they have given for this 2. For this 2 what is left? What is left? So they are given like this. Okay, 1. 1 is a root node. Then the left node is 2 and for 1 the right node is 2 again. Okay, and then for this 2 what is the left node? The left node is 3. What is the right node? The right node is 4. The right node is 4. And for this 2 again, what is the left node? It is 4. It is 4 and the right node is 3. Okay, so like this. Okay, like this they will give the input. Then you need to check whether it is symmetric or not. Are we clear? Are we clear? Can you try this problem? Yes, can you try this problem? Can I give it as an assignment? Yes. Same like your identical trees only, but small change will be there. That's it. Okay. And if you can see this problem, is this symmetric or non-symmetric? Is this symmetric or non-symmetric? You have the root node. You have the root node, same. And then 2. 2 is there on the left side. Here it is there on the right side. Correct. Left and right, it will overlap. And if you can see, here it is null on the left side. Here it is null on the right side. On the left side only. Whether it will overlap? Whether it will overlap? No. Here also it is there on the right side. Here also it is there on the right side. Right side. Attendance people, please stay quiet. Like in the end, again, it will be shared. Okay. Please stay quiet for some time. At least for next 10 minutes. Please. It's my humble request. So they are answering. I will miss out their answers. Okay. So again, it will be shared in the end. Please don't put the message in the chat box. Okay. So see here, 3 will be on the right and 3 is on the right. So it is not symmetric. This will not overlap because if I fold this paper, what will happen? This will go to the like it is on the right side itself. So if I fold this paper, it will come on the left side. It will come on the left side, not on the right. Okay, so it is not symmetric. It is false. Okay, so this problem you please solve it up. Okay, you please solve it up here. Okay, here in this you can write the code and you can check out the test cases. Okay, so otherwise if you're facing any issue, tomorrow I will let you know. Okay, tomorrow I will discuss this. Okay, and next one, this is about the binary trees. Okay, this is about the binary trees. Let me go ahead and discuss the binary search trees. Okay, binary search trees or else BST or else BST. So binary search trees, what will happen means like we will follow this condition. The root node, what is the data is there. Okay. For this root node, whatever is lesser than the root node, whatever is lesser than the root node, the data, what you are keeping from the next node should be on the left side only, should be kept only on the left side. And whatever is greater than the root node will be kept on the right side. Okay, will be kept on the right side. Suppose 100, 121, 90, 45, 165, 34. Okay. So now this 100 is the root node. 100 is the root node. And 121. 121 is greater than 100 or lesser than 100? 121 is greater than 100 or lesser than 100? Greater than 100. Should be on left side or right side? Should be on the inserted at the right side of this root node. Okay, 121. Okay, and then 90. 90 is lesser than 100 or greater than 100? 90 is lesser than 100 or greater than 100? Lesser than 100. So it should be on the left side. Okay. Then 45. 45 is lesser than 100 or greater than 100? Lesser than 100. So you should traverse to the left side. And then 90. You should again check with this root node as well. 90. It is lesser than 45 is lesser than 90 or greater than 90? Lesser than. So it should be on left side or right side? Left side. Right? So 45 is placed here. Okay. Then 165. 165 is lesser than 100 or greater than 100? Greater than 100. So you'll directly go to the right side. Then 121. 121, 165 is greater than 121? Yes. So we'll be placing on the right side. Again, we'll be placing on the right side of 121. And then 34. 34 is lesser than 100? Yes, correct. Lesser than 100. So you should go on the left side. Then 90. So 34 is again less than 90, right? You should again go to the left side. You should again go to the left side. Then 34 is again less than 45. Again less than 45. Then again you should go to the left side. You'll be placing the 34 here. You'll be placing the 34 here. So if you see now, like all the nodes, all the subtrees, if you consider this as your subtree, all the nodes, what is there on the left subtree is lesser than the root node. Is lesser than the root node, and all the nodes that were there on the right subtree are greater than the root node. Are greater than the root node. So this is nothing but a balanced binary search tree. Okay, balanced binary search tree. Okay, it is called as binary search tree because it contains only two nodes. Okay, it contains only two nodes. Like every node will have at least two nodes. Okay, at least two nodes. So it is called as binary tree, and it is called as search tree because it is called at least two child. Yes, every node will have at least two child. And then it is called as search tree because we are doing like this. So left is lesser than root data, greater than right data. Okay. So like this we will do when it is called as balanced binary search tree, when you are balancing it in such a way that is of format log to n. Okay, level should be of this format. So if you are having how many nodes here? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. 6 nodes. You are making the level as log to 6. See now, this is first level, second level, third level, and then this is fourth level, right? So you are making these nodes in four levels. So then in that case it will be binary history. Here it is not correctly balanced, but when it will be balanced, when you have the level, when it is balanced at the same level. Okay, when it is balanced at the same level, it is called as a balanced binary search tree. Okay, so how to insert a node into the balanced binary search tree? How to insert? Let me explain that pseudocode. How to insert into BST? How to insert? Why it is going like this? How to insert into BST? So you will be having the same again left node and then root and then left and then right. Correct? You'll be having the same again. So what you need to do basically when you are inserting, what you need to do, you should check. You should check first. Okay, I'm using this clear all drawings and then okay. So when you're inserting, what you're doing, you should be checking if first whether it is root is equal to null, whether root is double equal to null. Then what you will do, you should just return that. You can just return that new node, right? You can just return that new node of your value. Okay, new node of your value. Left will be null, right will be null. When the root is not null, when the root is not null, then what you will do? When the root is not null, when what you will do? So you will be taking a like a node. What is there as root? I'll take it as temp. Okay, I will take it as I will take it as temp, and then I will be starting a loop. Okay, I will be starting a loop. Nothing condition I will keep here. Okay, nothing condition I will keep it up here. I will take it as always true itself. Okay, then what I will do, if temp dot if your temp dot, so this one temp is root, right? Temp dot value is temp dot value is lesser than or equal to your data, is lesser than or equal to data. Then where you need to insert? When the value is lesser than or equal to data, where you need to insert, left side or right side? We should traverse to left side or right side? Lesser than or equal to data. So means this is lesser. No, data is our new part, right? Data is greater. When it is lesser means data will be greater, right? When it is greater, where you will move? You will move to the right. Temp is equal to temp dot right. You will move to the right. Okay. Else you will move to the left. Temp is equal to temp dot left. Okay, temp dot left. Okay. So you will move like this, and then what you will check? You will again check it up, right? If it is more like you will also check whether okay, temp is equal to temp dot right. You will move to the right, and then you will what you will do, if it is not lesser than still, if it is not lesser than still, so like you have reached the right node, the exact right node, then what you will do, you can directly place it up, right? Temp dot right. Okay, temp dot right is equal to new node. Okay, is equal to new node of your value, new node of your value, and then you can break it up. You can break this loop. You can break this loop. Okay, this is your if else condition. Okay, this is your if else condition. If tempo dot value lesser than or equal to data, what you are doing, you are moving to the right. Okay, you are moving to the right. Okay, you will also check this condition also while moving to the right. If you will check whether tempo dot data double equal to null. Okay, whether it is empty, then what you will do, you will directly place that, you will directly go to the temp dot right. Or else you will move to the, this is inside, okay? This is inside, okay? So this is if starting, okay? If temp dot data double equal to null, then you will move to the right. Else, if it is not equal to null, then temp dot right is equal to new node of value. Okay, when it is not equal to null, when it is not equal to null, you will move to the right. Otherwise, you will directly insert it. Okay. Else what is the condition? Where when it is greater than or equal to data. When it is greater than or equal to data, then you need to move in the right side. Again, you will be checking. Again, you will be checking if tempo dot left, tempo dot left not equal to null. Then what you need to do? You need to move to the, you need to move to the temp is equal to tempo dot left, tempo dot left. Else what you'll be doing, directly will insert the tempo dot left, tempo dot left is equal to new node of value, new node of value, and then you can break it up. You can just break it up. Okay, so this is the inserting a node into the BST. Okay, this is the algorithm you will apply for inserting a node into the BST. Okay, so is this understandable? Yes, yes, everyone. So I'll be sharing this code even in your notes. Okay, even in your notes, I will share this code. Okay, so you can observe this code, and the assignment 2 is for today is assignment 2 is for today is to go through assignment 2 is for today's delete a node from BST. Okay, delete a node from BST. Delete a node from BST. So here I have done the insertion. Here I have done the insertion. You need to do how you can perform the deletion. Suppose they are giving some data you to delete. Suppose tree node of some data they are giving to delete. Okay, some data they are giving you to delete. Then what you need to do? You need to search. You need to search where it is lesser than or equal to or greater than or equal to data. Your root node you need to check. They will give the root node as well as data. Root less than or equal to data. Your given data. Then where you should move? You should move on the right side. You should move on the right side and you will move and then you will delete it. Means you will equal to null. Some change you will do here. Okay. When it is greater than, what you will do? You will move to the left side. You will move to the left side, and then then you will put the null there. Again, the same thing only, but there will be some change. Okay, are we clear until this point? Yes, when it is lesser than or equal to data, what you are doing? You are checking whether it is null for traversing, basically. So if some data is there, when it is less than, so you are moving here, means it is null or not, you are checking. It is not null. Then again you will move to the right. If it is null, again you will move to the right. Okay. Again, if it is not null, it is not null. Then what you will do, you should move to the right. But here it is null. Directly what you can do, you can insert the data here. You can insert the data here. When you're inserting the data here, then you are breaking it up. Okay. So see the code in the notes. Once observe the code in the notes. Okay. And try to do this assignment of deleted node from BST. Okay. One final question. One final question from my side. So why we need BST? Why we need binary search tree over binary tree? Why we need binary search tree over binary tree is my question. Why we need binary search tree over binary tree? Answers, please. Answers, please. Answers, please. Why we need binary search tree over binary tree? Yes, exactly. So searching. So in the case of binary tree, if I wanted to search design analysis. So in the case of a binary tree, Suppose the data is like this. The data is like this. 10, 11, 12, 13, 14, 16. Suppose this is considered as binary tree or binary search tree. Is this a binary tree or binary search tree? This one. Binary tree or binary search tree? Binary tree or binary search tree? It is a it is a binary tree itself. Why? Binary tree itself. Why? It may be looking like binary search tree. See, left side, left side. Suppose if I'm putting 9 here, then it is called as BST. It is called as BST. Here it is BST only. Here it is BST only. But you see the left right subtree. You see the right subtree. See, it is greater. This is also greater. This is also less than. This is also less than. This is also greater. But the thing is, if you see, if you see this 13 is again greater, 16 is greater, 18 is greater, 14 is greater, 12 is greater, right? If now it is BST.
It's
Now it
9
is
o'clock.
BST. Now this is BST. Before it was not BST, but now it is BST. Okay. Suppose if I'm changing this to some 5, okay, some 5, and this one to 6. Now is this a BST? Yes or no? Now it is a BST or not BST? Can I get a quick heads up in the chat box? It is not a BST because 5 year, 6 year. Here it is balance. Here it is perfect 6, 18. But the thing is the binary, the left right side, all the nodes should be greater than the root node. But here you see 5 and 6 were lesser than the root node. So it is not called as a BST. It is not called as a BST. It is considered as a binary tree itself. Okay. So suppose I wanted to search 18. I wanted to search 18 in this binary tree. So how I will search it up? How I will search it up? Each and every node I need to compare, right? Left side, right side, until the right side and left side null. I need to traverse until left side is null. I'll be checking each and every node. And I will also check the right side. Either of the traversal you need to check. Either pre-order or post-order, any of the traversal you can take. And you need to keep on checking. You need to keep on checking. Means you will traverse each and every node. There are like 1, 2, 3, 4, 5, 6, 7, 8. 8 nodes are there. You will traverse all the 8 nodes. So what is the time complexity in this case? Big of n. If you wanted to search 18 or 19, what you will do? You will search around the all the nodes. Suppose this is BST. Suppose this is BST, not binary tree. Then what you will do? 19. 19 is greater than 10. So will you go on the left side or will you go on the right side? You will go on the right side itself. You will go on the right side itself. And here also 12. Again right side. Again right side. Here also 9, 14. 14 it is. So 19. So again right side. Again right side. Like this you will search. Means whatever what you are ignoring. What you are ignoring. This part full. Right. I will take another color. This part full you are ignoring, right? This part full you are ignoring. You are only traversing this part. You're only traversing this part. So is the time complexity increase or decrease? Will it increase or decrease in this case from binary tree? In the case of binary tree, it is big of n, where in the case of binary search tree, it will be log n itself. It will be log n itself. Means time complexity is efficient here or efficient here. This is efficient. So in the case of searching, binary search tree will be efficient. Binary search tree will be efficient. Are we clear until this point? Yes, everyone? Okay. Yes, everyone, are we clear? Okay. So today I thought of completing the graphs as well, but I am not able to complete this graphs topic. Okay. So graphs topic. Okay. So what I will do, tomorrow I will discuss the terminology and traversals, just traversals, and then one problem also if time permits. Okay. BFS and DFS I will discuss in 1 hour. Okay, 7 to 8. Okay, then you will have a test from 8 to 9, like 8 to 9 anyways, right? You will have a test, MCQ test of from 8 to 9. Okay, so in 1 hour I will discuss this traversals along with the code, and then if possible I will also discuss one LC problem. Otherwise I will explain the intuition, I will explain the pseudocode, and I will we will continue with the test. Okay, so this is only the topic that is left. We will continue tomorrow. Are we clear until this point? Yes. Yes, everyone. So what is assignment for today? What is assignment for today? Implementing. Implementing. What is assignment for today? What is assignment for today? So DP, I will take this up in the DP also. I will explain the intuition around the DP as well. Okay. No need to worry. I will explain the intuition around DP as well. Okay. Students will need these are many beginner students. So definitely this is important for them rather than DP, because if you have understood these traversals, then that only will apply in the DP only on also, right? So I will also one problem I will take it up, which is covering DP, and I will also do the intuition around this. Okay, Mod? Yeah. So I want you to implement like two problems, right? One is symmetric binary tree problem. Okay, symmetric binary tree problem. And the next problem, one problem I have given, other problem. What is that? Uh, I don't remember that. What I have given. Do you remember the assignment one? Assignment one, do you remember? One problem I have given. Okay, so practice around this problem. Symmetric binary tree I've given. The other problem also I've given. I forgot. Okay, so at least do this problem. Okay, symmetric binary tree problem, you do it up. And in the notes, I will share the other problem. What is assignment that is missing? I will share that up. Okay, so on that note, yeah, deleting a node. Correct, Chetan. Yeah, thank you so much. Good. So deleting a node. Deleting a node from BST. Right? Deleting a node from BST. So these two problems, please try to complete it up. So these are model questions which I have discussed in the current class. Okay. So on that note, thank you so much, guys. We'll meet again tomorrow in the last session. Okay. Good night, everyone. Over to you, Susmita.
Yeah, thank you, sir. Thank you so much. Yeah, as students, as you all know, tomorrow is the last day for this particular program, that is day 15. So we are conducting an assessment for 50 marks, 50 MCQ question. So as usual, Roshit sir is going to take a session till 8:15. After 8:15, I'll be sharing the assessment link on the same chat. Then you all should take a assessment. Okay. So the tomorrow class will be for 1 hour, almost 1 hour to 1 hour 15 minutes. So I request please inform your friends and make sure that you all join the session tomorrow without any fail, as this assessment will be based on your the topic has been covered in the like complete 15 days of program. Okay. Yeah, thank you all. So we will wind up for the day. We'll meet again by tomorrow. Thank you everyone. Good night. Thank you, sir.